All right, so today we're going to be talking about the chain rule. So, um, chain rule is pretty important for calculus because it helps simplify a lot of problems. And to kind of motivate it, let me go over this. So, let's try to find the derivative of this function y is equal to 3x squared plus 1 to the power of 3, right? Now, so far, without the chain rule, what the only way that we could find the derivative of this is to expand this function out. And so, we'd have to multiply 3x squared plus 1 times 3x squared plus 1, and then times 3x squared plus 1. And now this is going to be extremely tedious, right? To all of this just to find the derivative of this function. But essentially, the chain rule allows us to basically treat functions as compositions of another function. So another way we could treat this is we could treat this 3x squared plus 1 as some other function u. So u of x is equal to 3x squared plus 1, and then y is simply equal to u to the power of 3. So essentially, y is a function of u, and then u is a function of x, right? And what the chain rule kind of tells us is that if we have any compositions of functions, so if we have some like f of g of x, then the derivative of f of g of x is equal to f prime of g of x times g prime of x, right? And so what this kind of tells us is that more concretely, what it tells us is that when we want to find the derivative of functions that are composed of each other, right, we can kind of treat this outside. We can treat each function as its own separate entity and find the derivatives of their own, and then continually like expand outwards. And so let's sort of like see an example by applying it to our toy example of 3x squared plus 1 cubed, right? So we had y is equal to 3x squared plus 1 cubed, right? And let me treat this function y as a composition of two functions, right? So we'll call f is equal to some g to the power of 3, and then g is equal to 3x squared plus 1, 3x squared plus 1, right? And we've been told that the derivative of like this whole function y, which is f, which is equal, so y which is equal to f of g of x, right? We know that the derivative of that, so y prime is equal to f prime of g times g prime of x, right? So f prime of g, we know is just 3g squared, and then g prime of x is simply equal to, in this case, 6x, right? Right. So then in the end, our when we multiply those together and we substitute in the value for g, we simply get 3 times 3x squared plus 1 squared times 6 times x. So pretty simply, we found out that the derivative of this function is 18x times 3x squared plus 1 squared. And so essentially, what the chain rule allows us to do is we can treat complex functions as compositions of functions, and we can find the derivatives of them in a systematic manner to calculate the end derivative. And so, a trick that makes it easier to remember which derivatives we have to find and multiply out together. Let's say we want to find at the end the derivative of y with respect to x, right? And so essentially we can sort of, if we decide that y is like a function of u, which is like another intermediary function, right? Then we first find the derivative of y with respect to u, and then let's say u is a intermediary function of g, and then we find the derivative of g with respect to with we find the derivative of u with respect to g, and then g with respect to x, and then you can kind of treat it like fractions, and in a way that all of these sort of cancel out, and at the end you get dy over dx. So if that helps, like, remember which function or what derivatives to find and multiply together, this trick kind of can provide some intuition. But let's work through some examples of where the chain rule is useful. So let's differentiate this function y is equal to sine x squared plus x with respect to x, right? So clearly we have this outer function over here, which is sine, and then we have this inner function over here. So let's just first dealing with the sine. So if I treat y is equal to sine w, where w is equal to x squared plus x, then I can first find the derivative with respect, so I can find dy over dw, which we know is just cosine of w, and then I know I want to find dy over dx at the end, right, which is equal to dy over dw, because we created this intermediary function w over here, and then if we find dw with respect to dx, we can get our final value where we want the derivative of y with respect to x. So we already found dy over dw, and now let's just work on dw with respect to dx. And so this is a simple polynomial, and then the derivative of that, so dw over dx is simply 2x plus 1, and then in the end dy over dx is equal to cosine w, and then multiplied by 2x plus 1, right? And because we want everything in terms of x, let's substitute in the value for w. So we know w is equal to x squared plus x, and then so our final answer is 2x plus 1 times cosine of x squared plus x, and that will be our derivative at the end. To just make sure that we completely understand this, let's just do one more example. Let's see, what function should we choose? Let's use more trigonometric functions, and let's find the derivative of, let's call y is equal to tangent of 5 minus sine 2x. And so now, if you kind of look, there's multiple things going on. We can call the outermost function tangent of w. So let's just say tangent of w is equal to y. We can say w is equal to 5 minus sine of 2x. And then, or we can say tangent is equal to 5 minus sine of, let's call this z, and then z is itself is equal to 2x. And so we created these three functions, and we want to know at the end what dy over dx is, and dy over dx is first dy with respect to dw times dw with respect to z, because w is 5 minus sine z, and so it's a function of z, and then times dz over dx. And so multiplying all of these together, this is basically what the chain rule is. So we're basically applying the chain rule over and over again, removing each of these composed functions to come up with our final answer. And so the product of these three terms will give us the final answer. So let's calculate dy over dw. So tangent of w, so the derivative of that is just secant squared w, dw over dz, so minus sine z, so then we have to multiply by minus cosine z, and then dz over dx is just times 2, right? So, and then now let's substitute in our terms for w, or for, we want everything in terms of x, so let's substitute in the correct value. So secant squared times 5 minus sine z, but z is 2x, so this will be sine 2x, and then minus cosine 2x times 2, and then that will just become 2 secant squared of 5 minus sine 2x, and then because of the minus cosine. So times cosine 2x. So that is our final answer. And look how the chain rule made this complex looking function that it seems kind of hard without the chain rule to know how to differentiate. And we found a systematic way to differentiate this. So whenever we see compositions of functions, the first thing that we should probably keep in mind is the chain rule for differentiation.